All right, so here we are in Unit 9, where we are starting to talk about stoichiometry. It's a concept that goes along with the chemical reactions that we've been seeing and also the mole conversions that we did in Unit 7. So in this one, we're really combining the last two units into a single concept. Now, stoichiometry, I know that it seems like a very complicated word, but what it really is just a method that we use for calculating the amounts of reactants we need to start a reaction and the amount of products we can get out of it. And one thing that I want to point out right from the top is this word stoichiometry. I know that it has a CH right in there, and you're familiar with that CH making a ch type of sound, kind of like in the word cheese. But in this case, the CH will make a k sound. So that's why we say stoichiometry. It won't be stoichiometry. So make sure that you practice on that. Make sure you say stoichiometry every time. All right, and in this first section, 9.1, we're getting into ratios, and we're just relating the amounts, the moles of two different substances and how they are related to each other, how many you need for a reaction to happen, and then how you might have something that's left over or something that you don't have enough of. All right, so let's go ahead and get into it. So the vocabulary that you need to be familiar with is the mole ratio, the excess reactant, limiting reactant, and the theoretical yield. So now, when we talk about mole ratios, the first thing that we need is a balanced chemical equation. And just a short reminder of what we covered in the last Unit 8 is that a balanced chemical equation follows the law of conservation of mass. And what that means is when you have a chemical reaction like this with the reactants on your left side, the products on the right side, and they're separated by the reaction arrow, we need to have the same types of elements and the same number of atoms on both sides of the equation. So our left side needs to be the same as the right side when it comes to the number of elements and atoms, but those atoms can be connected and bonded in different ways. We can have different chemicals, different substances, but the atoms are still the same. So just a reminder, I want to make sure that everyone is clear on this one, is that in our chemical equations, we have the chemical formulas. These are the ones that tell us what type of substance we have. This is the identity of it. And the subscripts go along with that. We cannot change these subscripts that go behind each element. But what we can change is the coefficients that go in front of each type of substance. And this tells us how many moles of each substance we can have or what we need. So remember, for our mole ratios, we're going to be focusing on the coefficients, and this is where we get the ratio, or sorry, this is where we get the number of moles to set up our mole ratios. And all we're doing with a mole ratio is just like a normal ratio where we compare the amounts of two different things, two different substances, two different chemical formulas in these examples. All right, so if I wanted to pull an example and compare the amount of C2H2 that I need for my O2, I can just go to my balanced chemical equation and pull the coefficients of that. So I can say that for my C2H2, I would need 2 moles of it, and to match that, I would need 5 moles of oxygen gas, O2. And so as compared to my two reactants, that's saying that for every 2 moles of C2H2 that I want to react, I need 5 moles of oxygen gas to go with it. And we can also compare this to the products on the other side. So if I wanted to compare against C2H2 and compare it to my product of water, that's saying that for every 2 moles of C2H2 that I put in, I will be getting out 2 moles of H2O. The next thing that we need to consider is that for our reactants, we can have 2 different types. We can classify them in 2 different ways. We can either have an excess reactant or a limiting reactant. So where that comes from is that when we have a balanced chemical equation, it's very easy to say the perfect mole ratio, right? We're talking in theoretical terms. And so when we pull the mole ratio from a chemical equation and everything is perfect, we call that the theoretical yield. But in practice, it's actually really difficult to measure out an exact amount of moles of a substance in a lab. Alright, so our amounts are not always perfect. There's got to be a little bit of wiggle room in that too. And so what that comes down to is, especially if you only have 2 reactants, or you can have 2 or more reactants, but there will always be one reactant that we have more of. We have a little bit extra of it. And so actually this reactant that we have extra of, that we have in excess, is called the excess reactant. And because we have a lot more than we need, it's not completely used up. We will always have a little bit left over. And then the opposite side of that is the limiting reactant. This is the stuff that we run out of first. So let's see. Let's draw an analogy to sandwiches. We're going to be using sandwich ingredients instead of chemical equations to just put this into perspective a little bit. Something that's a little bit easier to understand. So I like to go to a simulation that I have on this where we can pull different things. So this is a simulation called PHET, and it's from the University of Colorado Boulder website that they provide this for us. But it's a very useful tool for trying out these different things and making it just a little bit more tangible on the computers. So let's see. For these chemical equations, again, you can have a chemical equation that is completely balanced, but taking it to our example of sandwiches, instead of thinking of a chemical equation, think of this more as a recipe. So in this recipe, say that we're making cheese sandwiches, we would need 2 slices of bread and 1 slice of cheese to make a cheese sandwich. This is our recipe, or in other words, it's our chemical equation that we need. So what that means for our reactants is that we need to put in 2 pieces of bread. So let me go ahead and put that in. 2 pieces of bread and 1 slice of cheese to make a sandwich. These are the things that we need. But notice that in this simulation, I can also mess with the number of things that I'm putting in. So in this case, let's say that we wanted to make a second cheese sandwich. We need to put in 2 more slices of bread. So let's go ahead and try that. 2 slices of bread and 1 more slice of cheese to do this. All right, but notice here that when I put in my bread, I don't get a sandwich left. Notice that on this simulation here, I can have my products, these are the complete sandwiches, and the leftovers, these are the incomplete sandwiches. So in this one, if I put in 2 pieces of bread and no more cheese, I can't get another cheese sandwich. I just have bread on this one. And this is what you see here that I have, for my leftovers, I have 2 slices of bread. And it won't be anything else until I put in another slice of cheese. So let's try that. All right, great. I have 3 cheese sandwiches left. So now notice here that, what if I just put in 1 more slice of bread? What if I'm running out, I only have 1 last slice of bread, but I still want to make another cheese sandwich. And let's say that I had enough cheese for it. So notice that even though I stacked it on the amount of cheese that I have left, because I don't have enough bread, I don't have 2 pieces to make another sandwich, I can't make any more sandwiches. And that's the idea of the limiting reactant. I don't have enough bread to make any more sandwiches. And so one thing that I need to point out here is that, in real life, you can get away with just making a single slice, making a sandwich with just 1 piece of bread. But in these simulations, we need to have perfect ratios. That means that for every slice of cheese, we need 2 pieces of bread. Without those 2 pieces of bread, we can't make any more sandwiches. And we can relate that back to the examples that we have for chemical equations. So here's the reaction that would make water, just combining hydrogen gas and oxygen gas. By the way, this would launches rockets into space. So I think it's a pretty neat reaction. But anyway, in this simulation, just what we're focused on is that we need to have the exact ratio. We need the exact number of pieces to go forward with this reaction. So again, I can put in, follow my chemical equation, follow my recipe of 2 pieces of hydrogen, and notice that in my products I still only have hydrogen. I haven't made any oxygen until I haven't made any water until I put in my oxygen. So notice here that if I were to put another molecule of water and 1 more molecule of hydrogen, notice here that I still can't make more water molecules, even though I have plenty of oxygen to make 2 water molecules. I don't have enough hydrogen, and without having enough hydrogen, I can't make more water molecules until I add more. So again, this is the idea of the limiting reactant. I'm missing some piece to keep me from doing my reaction more times.